All right, got a calculus exam coming up? I know. The words double integrals can sound pretty intimidating. But what if I told you they're actually your secret weapon? Seriously. Today, we're going to build your ultimate exam survival guide. We're going to turn this topic from something you fear into a tool that helps you absolutely crush those final questions. So let's just forget all the dry textbook theory for a minute. The best way to really get this stuff is to dive right in and tackle a problem you might actually see on your next test. We're starting with the practical stuff, the things that are actually going to get you points. Okay, so here's our challenge for today. How do you find the area trapped between two curves? We've got the parabola y equals x squared and the straight line y equals x. Now, you could probably solve this with a single variable calculus you already know, but there's a much more powerful and systematic way to do it, a method that works for way more complicated shapes. And that, my friends, brings us to our main tool for the day, the double integral. This is the big one. It's the concept we really need to get a handle on, not just for this one problem, but for a whole class of questions you're going to see about areas and even volumes. So, what even is a double integral? Look, at its core, it's just a really fancy way of adding stuff up. That's it. Just imagine taking the area you want to find and slicing it into a bajillion tiny little rectangles. The double integral is the magic tool that adds up every single one of those little pieces, we call them delta A, to give you the total area. Simple as that. You know, the best part about double integrals is that the process for solving them, it's called iterated integration, is super mechanical. It's like following a recipe. You always work from the inside out. Solve that inner integral first. And here's the trick. You just pretend the other variable is a constant, then you plug in your limits, and boom, the whole thing just turns into a regular old single variable integral that you already know how to solve. Okay, time for our first big exam trick. This is a pro move. You're going to get an integral on your exam that looks, well, it looks impossible. Absolutely brutal. But there's a secret weapon that can completely flip the script, changing the order of integration. And seriously, do not underestimate how powerful this is. Just choosing to do dy dx instead of dx dy, it can literally be the difference between a problem that takes you half an hour of banging your head against the wall and one you can solve in like 30 seconds. Just look at this example. The integral on the left, it's a total dead end. Trying to integrate e to the minus y over y with respect to y, it's a nightmare. You can't do it. But watch what happens when we just flip the order. Now we integrate with respect to x first. Well, that just gives us x, right? Plug in the limits from 0 to y, and you get y. And look at that. The y we just got perfectly cancels with a y in the denominator. All that's left is a super easy integral. It's the exact same problem, just transformed by looking at it differently. All right, let's add another tool to our toolkit. This one is a specialist, and it is a total game changer. Here's the deal. If you see a problem on your exam that involves circles or semicircles or anything, round, one word should just flash in your brain like a neon sign: polar. Polar coordinates. It can take a really messy problem and make it incredibly simple. So here are the key conversions you just got to memorize for the exam. X is our cosine theta, y is our sine theta. Simple enough. But the most important one, and I'm telling you, this is where everyone messes up, is that last one. That little area piece, dx dy, does not just become dr d theta. No. It becomes r dr d theta. Forgetting that extra r is probably the #1 mistake people make on these exam questions. Don't let that be you. Okay? Okay, so our toolkit is looking pretty good. We know how to do iterated integration, we've got the pro move of changing the order, and we've got polar coordinates in our back pocket for anything circular. I think it's time. Let's go back and finally solve that problem from the beginning. So let's take another look at our original challenge, the area between y equals x squared and y equals x. It doesn't look so scary anymore, does it? Now we have a plan. We have a process. Let's just walk through it step by step. First thing, we need to know where these two curves even cross. So we set them equal to each other. X squared equals x. That gives us x equals 0 and x equals 1. Perfect. Those are our outer limits, the constants. Now for the inner limits, just imagine drawing a little vertical line or strip inside the area. What's the bottom of that strip touching?
the parabola, y equals x squared. And the top, it's touching the line, y equals x. So those are our inner limits. From there, we just set up the integral, knock out that super easy inner integral for y, and we're left with a basic single integral for x.
And when you solve that final simple integral, what do you get? 1/6. That's it. A nice, clean, simple number from a problem that seemed kind of complex at first. See? That is the power of having a system. Okay, before we wrap up, I want to make sure all of this really sticks in your brain for exam day. So let's boil everything down into a simple, actionable checklist. Think of this as your game plan. The moment you see a double integral question, this is what you do. Number 1, always sketch the region of integration. Seriously, I can't say it enough. It is the single most important step. Number 2, figure out your limits. You can do this by imagining those little vertical or horizontal strips. Number 3, if the integral looks nasty, what's your first move? Try changing the order. It might just save you. Number 4, see a circle or part of a circle? Don't even hesitate. Go straight to polar coordinates. And finally, let's say it one more time so it's burned into your memory. Don't forget the extra r when you switch to polar. It's r dr d theta. This checklist right here is your key to getting these problems right. So with these tools, you can pretty much find the area of any 2D region they throw at you. But this kind of leads to a bigger question, doesn't it? What happens when we jump into 3D? How do you find the volume of a sphere, or a cone, or some other crazy 3D shape? Well, that's a story for our next explainer.